I hope I am audible. Can you please confirm? Am I audible? Hello. Okay, yeah, fine, thanks. So let's start the live session for week 5. Okay, okay, I'll wait for a few minutes and then we can start. Okay, I think we can start now. Welcome to the live session for week 5 for the course Semiconductor Device Modeling and Simulation, which is taught by Professor Vivek Dixit from IIT Kharagpur, and I am Anant Singhal, a PhD student from IIT Jodhpur. And today I'll be assisting in solving some of the similar assignment problems that have been given to you in your week 5 assignments. So if we go towards the course outline, I hope you have already seen all the videos and we have covered the basic part of the semiconductor devices, that is uh, the band structures and the doping of silicon. And in the last lecture, we studied about our first device, which was a p-n junction, and we talked about it thoroughly in the equilibrium condition, and we were not able to cover the non-equilibrium case or the actual IV relation that we have for the p-n junction. And in this week, what do we have? We have this one more device, which is what we call as BJT, or the bipolar junction transistor, for this particular week. So what we'll be doing, we'll be starting with the very basic derivation of the p-n junction, and in this particular lecture, I'll be telling about the BJT structure and how does it actually work, and what is the difference in the structure of a BJT as compared to a diode. Um, and then we'll be covering some of the metal semiconductor contacts, which is one of the important topics, I would say, for this particular lecture. So we have both Schottky and ohmic contacts in the course outline. So we'll be covering these two uh, particular topics also. So in the last class, if you remember, we ended up with a even with a hetero structure, but with the same type of doping. If you remember, we ended up with a n plus n junction, uh, and we discussed that we'll be starting with a very basic question. Maybe we can take one more p plus or p minus p junction, and then we'll quickly move towards the application of voltage in any of the p-n junction. So let's quickly do that. I think it is accessible, or I hope you have already yeah, I hope you have already understood the last concept, that we figured out that the VBI of an n plus n junction was always coming out to be VTLN, and D1 over ND2, whichever is greater, should come above in the numerator. So let's take a question similarly, which is a question related to a, let's say, a P minus P junction. So P minus P junction means, let's say, P minus means we have a lesser doping, so I'll not Na minus, I'll write this as, let's say, Na1, which is, let's say, for example, in this case, not 15, let's take it 17, and let's say Na2, which is the smaller doping. Let's say this is for P minus, this is 10 to the power 15. So these are the two doping. So for P minus, we minus means we have a lesser doping. So for P minus, the doping is this. For P, the doping is this. Now again, we are at room temperature. We know that the Vt by Q or Kt by Q is at room temperature is 24 millielectron volt. So again, the question is, we need to calculate the VBI in millivolts. This is the question. So again, what you can do is, you can again quickly make a band diagram of this particular P minus P junction, and now you will be able to see that what is the actual VBI. Is it the difference in the Fermi level of the P plus or P minus, whatever is the question, and or is it the addition? So I would suggest you quickly make the band diagram, and let me know what is the final formula that you are getting for the VBI for this particular type of junction. Is the question clear to everyone? Oh. Yeah, so if you make a band diagram, you will be able to understand what exactly VBI is, and that will help. Similarly, we have done it for n plus n junction in the last class, you remember. So you can make a similar diagram, and it will help you in analyzing the formula and how it is coming out to be the difference or the addition, whatever it comes up with. So maybe I mean, the final goal is to calculate the VBI. If you can calculate it first, that would be fine. So maybe you can take 2-3 minutes and let me know your suggestions in the chat box. Okay, so let me also do it parallelly. That will maybe help. So again, we have a P minus and a P junction. So for P minus, so we only need to understand the main things, that where will be the exact Fermi level. Let's say these are the two materials. Let's say this is P minus, this is, yes. For P minus, so minus means we have a lesser doping. So for P plus, it will shift more towards the valence band. Minus means we have a lesser doping. So let's say, yeah, yeah. No, no. So let me make. So as I said, for P minus, it will be far away from the valence. Let's say this is the Fermi level for P minus, and for P, it will be somewhere here. So the higher Fermi level, the flow of electron is always from higher to lower. So the electron will flow from P minus to P. Is this clear? Because in P minus, we have a lesser doping. So that means we have the Fermi level which is far away from the valence band as compared to this. So that means we have to shift this down to make the final band diagram. So if I try to make it, so Fermi level is still aligned because we have the equilibrium condition. So let's say this is the Fermi level, and now your EC will go up and down. Something like this will happen. Sorry for the bad drawing. Yeah. So now here, if you see, the total change is this only. So if I calculate, so this is the EI, this is the EC, this is the EV, this is the EF. So this is, let's say, 5P. Let's say I'm denoting this as 2, and this is nothing but 5P1, and this is your VBI, the actual difference. So let's say this is QVBI. So in this, if you see it clearly, your VBI is coming out to be 5P1 minus 5P2. This was the main discussion that we had, that it is a minus, not a plus, because in the case of PN junction, it was a plus. So if you just put up the values of 5P1, we already know now. It is VT ln Na by Ni. So P1 is the lesser one or greater one? The greater one, so I have kept it as 1. So this is Na1 minus VT ln Na2 by Ni. So if I apply the law of transformation, it will come out to be VT ln Na1 by. So now we have already the value, so it will be 0.062 times ln 10 to the power 17 by 10 to the power 15. So this will come out to be 0.26 ln 100, so which is 2, which is 0.052 times 2.303. So this should come out to be. So I'm getting 0.119 volts. So now, I mean, the whole point of telling all this was, if you remember, in the PN junction, we had the VBI, which was VT ln Na and dy Ni square. Then we also did a N plus N junction, in which the VBI was VTLN and D1 by ND2, whichever is greater will come up. And similarly, we also did a P minus junction in which the VBI is VTLN Na1 by ND2, whichever is greater will come up. So this is the summary of all the junctions that we are studying from the previous class. I hope all of this is clear, and this is all applicable only at equilibrium. We have not applied any voltage as of now, and we were at thermal equilibrium in all the cases that we have studied. Is this clear? Okay, so let's move to the next topic then. Sorry? Oh, yeah, yeah, fine. Okay, so let's move ahead. Now, for the first time, what we'll be doing, we will be applying some bias in the PN junction. So till now, we were only worried about the equilibrium. So now, we'll be starting with the, because the reverse biasing is more important. So reverse biased PN junction. So in a very basic term, what do we, I mean, what does the reverse bias means? Can you tell? So this is, let's say, a PN junction. So what do you think the reverse biasing of this PN junction means? Yes, yeah, that is correct. So in the P side, what we do is we apply the negative voltage, that is the reverse of the P, and the N side we apply the positive voltage, which is the reverse of N. So now one thing that we are sure at now is that we have a certain depletion region in the PN junction. That is at equilibrium only without even applying any voltage. So at the end P side, there will be the acceptor ions, and at the end side there will be this donor ions. This we already know even without applying any of the bias. So what do you think will happen when we have a negative voltage applied here? So let's say we have a negative charge here, we have a positive charge here. So here the majority carriers are holes, right? So what do you think when we apply a negative voltage will happen to the holes? Yeah, so the holes will be getting attracted towards the negative bias, and due to which the junction towards the P side will increase. Similarly, if I say for N type, the majority carriers are electrons, and we have applied a positive bias, so they will also feel a force towards this positive charge, and the depletion or the barrier towards the N side will increase. So this was the case when we were at equilibrium, but now what do we have? We have an increased depletion width. So this is the new depletion width that we have, and after applying a certain reverse bias voltage, which I am calling, let's say, as VR. So VR means the reverse bias voltage. So let's try to make a band diagram now of this. Since we have applied a voltage, so now the Fermi level will not align. There will be a change in the voltage, right? So similarly, there will be a change in the Fermi levels also. The change in Fermi level always denotes the application of any voltage. So let me try to make the band diagram of this. So let's say we already know that this is the P side, and let's say this is the N side. Now we already know that this is a junction, or this is a diagram for the PN junction. So this was the case when we were at equilibrium. I mean, we had a single Fermi level. Uh, if I try to make that Fermi level also, which was something like this, I'll delete this line. But yeah, this was the case when we were at equilibrium, right? So now, but at now we are not at equilibrium. We have applied a certain bias. So what will happen now is we have a change in the Fermi level. So let's say this is the P. So this is what I'm denoting as EFP, and this will be the N. Because we are reverse biasing, so your Fermi level will actually go away from the conduction or the valence band on either side. So now if I try to have this extended lines, so this difference is actually your applied voltage. The Fermi level always tells you about the difference between the applied voltage. So this is what we are calling as VR. And here the total difference is still, let me extend these lines. The total distance is still this, or the total VBI, I would say. Not the VBI, sorry, VBI was the case at equilibrium. So let's say this is V total. So this is still V total. And this we already know, this is phi P, and this, sorry, and this is phi N. So initially, if you remember, I mean not initially, but in equilibrium, we had a VBI, right? Which was a difference of phi P, or we have, which was the addition of phi P plus phi N. So can you tell what will be the V total by seeing this Venn diagram? So it should be phi P plus this VR plus this phi N, right? And this phi P plus phi N, we are denoting this as VBI in equilibrium, if you remember, plus VR. So now actually what has happened, the actual voltage which was only VBI has been converted to the VBI plus the reverse bias voltage. That is the difference is that has come into the equilibrium. Is this thing clear? The thing that we have just done. Any, okay, so if this is clear, so if you rem yeah, 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 yes, exactly. So you see at equilibrium these two lines, this line and this line were aligning, but now we have a difference here. So I just made a band diagram before when the Fermi level were aligned, so I don't want to ruin this. So if you remember now for ideal p-n junction, that means at equilibrium. So if you remember, we also derived a formula for W, which was 2 epsilon Si by Q VBI 1 by Na plus 1 by Nd. So now this is same for reverse bias. So this will change to, because the overall VBI has now changed to VBI plus VR. So your W will change to, could you please mute your mic? So this will change to VBI plus VR 1 by Na plus 1 by Nd. So we can clearly see here that your equilibrium width was something multiple or the direct proportional of under root VBI. But after applying the reverse bias, it is now VBI plus VR. So from mathematics wise, we can also see that your width is increasing. Your depletion width is actually now increasing. And similarly, we also studied about the Emax or the electric field that we are discussing. That your Emax was nothing but, if you remember, it was QNDXN, sorry, over epsilon, or it was also equals to QNAXP over epsilon. And using this, we came to know that, if you remember, it was NDXN is equals to NAXP. So now this was nothing but, if you remember the plot, it was nothing but this electric field. This is Emax and this was W. So now what we know is phi x, or the voltage, is nothing but the integration of the electric field, right? And integration is nothing but area under curve, right? So what will be the area under this curve? What is the formula for a triangle? It is nothing but half times base into height. And we have just calculated Emax, and sorry, the potential that we have just seen, it is nothing but VBI plus VR instead of VBI. So I can keep this equals to VBI plus VR, and from this What can we say that your Emax is can also be written as, since this is negative formula, so let me write negative also. So we can write this as 2 VVI plus VR over W. Is this thing clear? Okay. So now since we also have a depletion region, so there are two more things that comes into the picture. The first major thing is the junction capacitance. So what is the very basic formula of junction capacitance or the capacitance? Yeah, that is one. There is this dq by dv, or since we are talking about junction which is having a certain depletion width, it is, if you remember, this is the basic formula that we study. Yeah. So in this, what we do is we always keep the junction capacitance divided by the area. So this is nothing but farad per centimeter square or something. So we always normalize the capacitance by area, and the formula for that is epsilon by d. And here you can see epsilon by d is the distance between the plates, right? So which is nothing but the depletion width. Is this thing clear? Yeah. So if this is clear, then what do we have? We have this junction capacitance as epsilon by, so W we have just derived, so it is 2 epsilon Si by Q. Then we have VBI plus VR, so I'm still talking about reverse bias, and this is 1 by Na plus 1 by Nd. So you can cancel out this epsilon, and from this your junction capacitance will come out to be, if you just do some calculation, it will be Q epsilon S by 2 NAND over Na plus Nd, and this is 1 by VBI plus VR. So now the main thing that you see, if I can say that at equilibrium we have that capacitance which is Cj naught, which is nothing but Q epsilon S by 2 NAND over Na plus Nd, and at equilibrium it will be only VBI, right? So if I can see this term as Cj naught, which is this, so I can write capacitance as Cj naught divided by 1 plus VR over VBI. So this is a very important relation which holds for the calculation of junction capacitance of any reverse bias PN junction. So reverse bias only, why we are talking about reverse bias, because the actual depletion width or the nominal depletion width that we have comes only in the after the application of reverse bias. So this is a very important formula that you will be studying. So now from here what we can see is, so we know if we increase the reverse bias, what will happen? More of the reverse bias means more the depletion width, and more the depletion width means lesser the capacitance. So we can also see it mathematically now. So this was all about reverse bias. Is there any doubt in this reverse bias? Yeah. So here what I was saying is, if I apply more reverse bias, we are having more width. I also explained through the diagram. And more width means if I see this formula, if I increase this denominator, your capacitance will decrease, right? So the junction capacitance will decrease. Yeah. If you increase VR, you know your width will increase, right? If I say I explain from this diagram. So so your if your width will increase, then we know your capacitance is nothing but epsilon by W, right? So this width will increase and your, yeah, capacitance will decrease. That is what I wrote. Yeah. Is this clear? Okay, so let's also quickly see the forward biasing, because the equation comes from the forward biasing only. So we'll be now seeing the forward bias PN junction. So again, now we are doing the forward biasing. So I mean, you must have understood that the your V total will be something VBI minus the V applied or the forward bias, right? Because in forward bias, what will happen? Your depletion width will decrease. So forward biasing is nothing but, so this is P, this is N, and this is, let's say, the depletion width. And if I apply a forward bias, which means, what do we have? At P, we have the positive, at N, we have the negative. So actually, your holes will be repelled or forced towards that, and your width will become something even more thinner. So this will be your new depletion width, right? So even if we try to make the band diagram to explain or to understand it more, so now let me make that. So let's say this is, yeah. So what do we have is we have the EI. So we have this. So we know that this is phi P. Let's say this is phi N. And the change in these two only is the applied bias, right? So this is VA. And now your actual V total is this. And your V total is this also. So now what we can clearly see is that the V total is nothing but phi P plus phi N minus VA. That means VBI minus VA. Is this thing clear? Okay. So using this only, we calculate, or since we left the important topic of this ideal p junction current equation, so using these only we get to know the final current equation for the p junction. And how do we calculate it? In the p junction, we know that we are only caring about the depletion. So let's say this is minus xp, this is xn, and let's say this is 0. So what we are more interested in how the minority carriers react, because it is all about the minority carriers in each of the region once we are forward biasing. So there is an exponential relation that comes. So this is nothing but the carriers, the holes in the n region. So whatever I am writing in the subscript is actually the region. So this is n side, this is p side. And similarly, there is exponential decrease here also. So this is nothing but npx. That means this is the minority carriers or the number of electrons that are present in the p side. And this is this is the number of holes which are present in the n side. That means minority carrier concentration. So both pnx and npx are the minority carrier concentration. And if you do some derivation, I will not do the complete derivation, but I'll let you know how do we do it. So your Pn as a function of potential comes out to be Pn naught, which is without applying any bias, plus Pn naught. Yeah, yeah. So what I was saying is this Pnx and Npx are the minority carriers. So now what we are doing is if we are applying the, let's say, the forward bias. So what is happening? Your minority carriers, let's say, let me make it here clear. So let's say this is a negative charge, right? So once you are applying the negative charge, what is happening? Your electrons are getting repelled, right? Your depletion width is decreasing. And at the same time, your minority carriers, which are the holes here, are also getting recombined, right? There is a generation and recombination that is happening. So now what I'm trying to say here is this relation is actually exponential in nature, and this P and X looks something like this. So there will be more minority carriers at the junction, and as you go away from the junction, they will always tend to reduce. And similarly, it will, yeah, this is on the forward bias. Yeah. So PNX will be the equilibrium case plus. So if you do some derivation, it comes out to be something like this. Xn minus X over LP, which is the diffusion length. And this always comes when x is greater than or equal to xn. That means in the n side. And similarly, npx, if you do, it will come out to be np naught plus. You can see the derivation in detail. Maybe it is in the lecture by Professor Vivek Dikshit. So it will come out to be xp plus x over ln, and this only holds when x is less than that of minus xp, that is on the p side. And once we have this concentration, we only need to calculate the current, right? So current density, if you remember, it is nothing but it is p plus it is j n side for minus xp. We are only interested in the minority carriers, as I said. And if you remember, I already explained about you that there are two components of current. One is the drift and one is the diffusion, right? So drift current we already studied, it was something nq mu e, if you remember. And the diffusion part was nothing but it was something dn over dx and all those things. So this was for n, and for p it was dp over dx. For p it was pq mu e, something like that. So now what is happening, because we are studying about the PN junction. PN junction major phenomena that is happening in that is helping in getting this current is, can you tell, it is either drift or diffusion? Yeah, because in the PN junction there is a very huge gradient that is from higher concentration to lower concentration. So what we are majorly interested in is the diffusion. So if I try to calculate the JPXN part, it will only be the diffusion part. So since drift is very less, so I'll write the diffusion formula only. So it is Pnx over dx, and Pn comes from here. So if I put this Pn here, we will get a term for Jp and Jn similarly. So your Jp, let me write, comes out to be QdP Pn naught over Lp exponential of V over Vt minus 1. And similarly, if you do the diffusion part for N type, so it is minus xp, it will come out to be Qdn Np naught over Ln exponential Va by Vt minus 1. And your current density will be nothing but the sum of these two. So it will be Q exponential of Va by Vt minus 1 dP Pn naught over Lp plus Dn Np naught over Ln. So this is your final relation, and in short what we write this as J is equals to Js exponential of V over Vt minus 1. And here Js is completely this term, which is the current density. So Js will be this dP Pn naught over Lp plus Dn Np naught over Ln, and times area also, because whatever we are discussing was the current density. Sorry, not the area. Area will come in the current part. So we also write this as I is equals to Is. So this is the equation that you study in books. It is Va minus Vt. So this is the ideal PN junction current equation. And we have already established. So this is exponential in nature, as you can see by the mathematics. So if I try to plot this, sorry. So in the forward bias, after certain on voltage, this is exponential, and in reverse bias, it looks something like this. So this is what we call as the reverse saturation current. That is the IS part. And this is the exponential nature. And at same time, there is a breakdown also that happens in reverse bias, which is the V reverse bias breakdown voltage. So this is the plot that you also see in the in general in the books. So this is from where it comes from, and if you want a very detailed derivation of this, that how this Pn and Npx has come from, you can also go through the lecture from Professor Vivek Dikshit. So he must have explained how these two terms are coming from. So is there any doubt till now in the equation? Okay, so let's quickly see one more term and then we'll quickly go towards the problems. So one more thing that is very important is to see the temperature effect. So what will happen if we, let's say, increase the temperature or decrease the temperature? So we have this formula in our hand now, which is I is S exponential of VA minus VT over minus 1. And we know this IS is nothing but AQ dP over LP plus Tn over ln Na. And how this Nd and NaS come? So I have just done that. So we know that Pn is equals to Na square, right? If you remember. So Pn naught is nothing but Ni square by. So since we are only talking about minority gases, so this will be Nd and Np naught will be Ni square by Na. So if you do this, it will come out to be something like this, and it will come out to be Ni square will be common. So now from here we can clearly see that there is one term which is temperature dependent, which is in exponential, and Is is also a very strong function of Ni square. And if you remember, we did a derivation for Ni square, which was NC exponential of minus Eg over 2 kT. Sorry, it was not 2. It was Eg over kT. For Ni, it was 2 kT. So now what we can clearly see now, Ni itself is a very strong function of temperature, right? So as I said, so Ni square is, since Nc and V are also dependent upon 3 by 2 temperature, so Ni square is something A naught T cube Eg naught over kT. So Ni is a very strong function of temperature. So in general, what happens is for every 10 degrees Celsius or 10 degree, I would say, not Celsius, rise in temperature, Is becomes double. So what I'm trying to say is, let's say reverse saturation current at time, or sorry, temperature T2 is equals to times 2 T2 minus T1 by 10. Are you able to understand this formula? So this is again one important relation. So if there is a difference of 10 times in the 10 degree in the temperature, your IST will become twice of that of the actual reverse saturation current. Is there any doubt in this? Okay. So if not, let's go towards some of the problems now for from diode, and then we'll quickly also wrap up with the BJT and the PN junctions. Sorry, metal semiconductor content. So this is the problem. We need to calculate the forward bias current of an ideal PN junction. Forward bias voltage is given, reverse saturation current is given, and thermal voltage is given. So this is very easy. Everything is given. This is the formula. So let me write it there only. I is equals to Is exponential of V over Vt minus 1. So quickly let me know the value. Maybe you can take 2-3 minutes and let me know the value in the chat box. Any answer? So this is 2.5 10 to the minus 10. Exponential of forward bias is 0.4. VT 0.0259 minus 1. So no, it should be greater than 14. So since this is 259 by 4000, it should be less. Oh, sorry, it should be more. So I'm getting the answer as 1.27 milliamps. You can check the calculations later also. This is what I'm getting. Let's move ahead quickly. So this is the next question. It says in an ideal P junction which is operated at 300 again. So the VT value is again the same. The magnitude of the reverse bias voltage required to reach 68% of its reverse saturation current. Is the question clear? So it is asking about the reverse bias voltage. The question is what is the voltage that is required so that the final current will be 68% of the reverse saturation current. Is the question clear? No, no, no. It's not temperature dependent question. It is asking you the voltage when the reverse saturation current becomes when the total current becomes the 68% of that. That means this is the formula, right? Exponential of V over Vt minus 1. So it is saying when this current will be equals to 68% of Is, what is the value of this voltage? This is what the question is asking. So this would be 0.68 Is is equals to Is exponential of Va over Vt minus 1. So Is you can cancel and you can calculate the Va. Vt is 0.026. So that Va will be the answer. Quickly, and the answer is in millivolts. So quickly do the calculations and let me know the answer. So this should come out to be, since this is minus negative voltage, sorry, I'm not We just seen that. So this should be 0.026 ln 0.32. So you can again check the calculations. I've done it. So it is coming out to be 20. So it will come out to be negative because this is reverse bias that we are talking about. 29.62. Yeah. So which is option C. So let's go ahead. So now the next. Oh yeah, sorry, I was on mute. I did not know. So yeah, it's 29.62. We have done the calculation. So let's move towards the next problem now. So in this problem, it is written in an abrupt p-n junction. We have the doping concentration on the n side, which is this, on p side, which is this. So n side means Nd, which is 10 to the power 16. P side means Na, which is 9 times 10 to the power 16. Assuming the p-n junction is reverse biased and the total depletion width is this. Calculate the width on the p side. So first of all, tell me by just by seeing the doping, which will be on the higher side? Is it XP or XN? Yeah, so that is correct. So that means XP will be lesser than that of XN, right? So that means we can clearly neglect these two options because total is 3, so uh, the P side cannot be greater than that of XN, right? And just to solve this now, the formula we already know, NP NDXN is NAXP. Right, so what do we have? And we know that W is XP plus XN. So what we can see is XP plus XN is 3 micrometer. It is already given. So that means, and also from this we can clearly see that ND is 10 to the power 16, XN is equals to 9 XP, right? Because the doping is 9 times. So if you put ND here and NA here, it will be XN is equals to 9 XP. So using this, we can write this as XP plus 9 XP equals to 3 micrometer. That means 10 XP is equals to 3 micrometer. So XP will be 0.3 micrometer, which is option B. Okay, I hope this is clear. This is straightforward now. Okay, so now we have one more problem. It says at 300 Kelvin, again at room temperature, diode of current 1 milliamps. So the current is given through a certain germanium diode requires a forward bias voltage of this. So the voltage is also given. Whereas a silicon diode requires a forward voltage bias of this. We need to find the ratio of reverse saturation current. Okay. So since we have different diodes, so let me tell you. So the ideal junction diode equation that you see, it was something like this, right? VA over VT minus 1. This is ideal. But to capture the material effects, the final equation comes out to be VA over eta VT minus 1. So this eta depends upon material. So for, as the question said, for silicon, eta is equals to 2, and for germanium, eta is equals to 1. So this is here mentioned. So this eta we need to keep in mind, and we need to find the ratio of the reverse saturation current. Is the question clear? Is there any doubt? Okay. Yes, yes. No, no, eta is given. You have to calculate the ratio of IS. So yeah, let me try to explain. So according to the question, the current is equals to the reverse saturation. So let's say I'm talking about silicon. It is exponential of this 0.718. 0.718 over 0.026 minus 1, and the current, the same current for germanium, it's exponential of this 0.4135. So yeah, this is 2 VT, not 1. For germanium, for silicon eta is 2, right? 2 VT, let me write. And this is 2 VT, and this is 1 VT. The question is asking about the ratio of silicon over germanium. Is it clear? So it will be nothing but exponential of 0.718 over 2 VT minus 1 upon exponential of 1435 over VT minus 1. So this means exponential of, so 2, so if I do it is, so 1 I'll neglect because exponential terms is anyway very high. So it will be 0.359 minus 0.1435 over VT. So this will be the answer, and VT I can write the direct value 0.026. So if I do it, this is exponential of 5, 1, 2. So this is exponential of 55, 8 point something, 8.288, and this is 3.99 times per 3. Any option like that? Yeah, so the closest option is option C. So option C is the correct answer. Is it clear? The calculations? Okay, so let's move ahead. This we have already done. This was the N plus N P junction. So N is the lowest, N in middle, P is this. So A was the correct answer. So I'll not do this again. I hope you remember already. Okay. So now the next problem is calculate the built-in potential for the PN junction diode, and the electric field is already given. So how to calculate the phi x? It is nothing but what? Area under curve, right? Because the electric field is curve given, so it is E dx. Yeah, exactly. So quickly let me know what is the answer. So it should be half into 1.3. So this is a micrometer. So I'll write in centimeter minus 4, because this is in centimeter into 10 raised per 4. So that should be 650 millivolts, which is option B. Okay, so BJT. Okay, so let me quickly explain you the concept of BJT also, since we have a question of BJT. So this is a more realistic question. So BJT is nothing but like two diodes which are connected together. So we have two types of BJT. One is a NPN BJT and one is a PNP. So it is a three-terminal device instead of diode like a two-terminal. So we have either NPN or a PNP. So if you see, if you see in depth, so this is one diode and this is one diode. This is one diode and this is one diode. So BJT is kind of like two diodes connected together, but not exactly two diodes. So what exactly happens in a BJT is BJTs are like a, so as the name suggests, sorry, BJTs. bipolar. That means it allows current to pass through both the sides. Junction, transistor. So it is a transistor, not a diode now. So transistor is nothing but transfer of resistance. That means it pass, let's say it has a low input resistance and it has a high output resistance. That is low to high. Transferring of resistance is what actually the transistors do. So BJT is nothing but a three-terminal device. So as I said, it is of two types. It is either NPN or PNP. So, and it has three terminals, which are namely base, collector, and emitter. So the input is base, the output is collector, and the third terminal is emitter. So whenever the current is going out, this is NPN, and whenever the current is coming inside, this is again base, emitter, collector. This is PNP. So now let me tell you some of the very basics. So we have, as I said, we have three terminals, emitter. So what we do in emitter, what we do, we generally dope it very highly. For base, what we do the light doping here. So this is lightly doped. And collector is in between, which is moderately doped. So now if I try to make, let's say, a PNP, so I'll try to explain the reason. So one thing is that the base that we make is always very narrow, and the collector that we make is always very high. That is the largest area is collector. So why? So this is, let's say, emitter base collector. So we have two voltage sources now. So this is how the connection of BJT works. So we have already seen the band diagram of this. So now it has four regions of operation. So the BJT can either work in cutoff, saturation, active, and inverse active. So inverse active in general never study. That means it acts as a attenuator. So in that we have emitter junction, we have collector junction. So if both the junctions are reverse bias, that means both the diodes are reverse biased, right? Then it acts as a cutoff, that is off switch. If both junctions are forward bias, then it acts as a on switch. That means the diode is on. If your active region is forward bias and your if your emitter is junction is forward bias, that is VB is forward bias and VBC is reverse bias, then it is amplifier. So this is the most important region that we are using it for amplification, right? So this is the most important region, I would say. And inverse active is this, and it acts as an attenuator. That means it is actually reducing the gain. So these are some of the very basics of BJT. So that question can actually be done in a very on the understanding of diode also. It says identify the correct relation between the built-in potential at base collector and base emitter for a NPN. So as I said, let's say this is NPN. So let's say we know what is diode, right? So this is one diode and this is the second. Yeah, let me try to explain. You will get able to get the correct answer. So this is emitter, this is base, this is collector. So now I just said emitter is heavily doped, right? And your collector is moderately doped. So what is the built-in potential for? So the question is asking about the built-in potential, right? Built-in, right? So built-in means for, let's say, for base collector, which is emitter base collector. So for VBC, the built-in potential would be, what is the formula for built-in potential for a diode? VTLN, right? This is the formula, right? So I just said for a BJT, emitter is heavily doped, whereas collector is moderately doped. So can you say that for VBC? Oh, sorry. Yeah. So can you tell whether VBC is higher or VBE will be higher? So which is heavily doped have a higher VBI or a lower VBI? So the common terminal is yeah, heavily doped means it has it has high doping. That means the VBI will be higher or lower. So if this value is higher, then your VBI will be lower. Hmm. Yeah. Yeah. So emitter is heavily doped and collector is moderately doped. So what do you think? Which will be higher, VBC or VBE? The question is asking that the built-in potential at which junction will be higher. Or, yeah. So it is like this, right? VB is greater. So what is the answer? Option D is the correct answer, right? Are you able to understand this? So this we have done on the understanding of diode, not BJT. And for BJT, I've already explained you the reasons that we have cut off and all those things. So you can see that again in the lecture on the YouTube video also if you want. The BJT is explained very thoroughly maybe in the lectures, so you can check those also. Is it fine? Okay, so let's move ahead quickly. Okay, so this is again a very straightforward question. It says a P junction diode built-in potential is zero point 0.8. The depletion width is so potential built-in potential is given, which is VBI, which is zero point 0.8, and the depletion width is 2 micrometer. When the reverse bias voltage of 1.2, so VR is 1.2, the depletion, the reverse bias, sorry, oh, so the depletion width is 2 when the reverse bias voltage is 1.2. So now it is saying that the depletion width increased to 7.2 when the reverse bias voltage is, yeah, sorry, yeah. So when then the depletion width increased to, oh, okay, I got it. Sorry. If the reverse, yeah, so we need to calculate this actually. So what will be the width? I just said what do we have? We have a relation of VBI plus VR, right? If you remember, we did this derivation. So what we can do here? So for the first case, it is zero point 0.8. So W1, let's say, it will be proportional to 1 by zero point 0.8 plus 1.2. Yeah. And W2 will be proportional to zero point 0.8 plus 7.2. That means W1 by W2 will be nothing but under root 8 by under root 2, right? Is there any doubt in this? Is there any doubt? So this will be 4 under root 4 means 2. So that means W1 will be twice of that of W2. So W1 we already know it was 2, right? Yeah. So the final width would be, so if we increase, it will be 4. So the correct answer is option D. Okay. So this is again a straightforward question. The resistivity of two sides are given. So you can take this problem as a homework. You can quickly take the screenshot of it. I hope you already have taken the screenshot. So you have to calculate the built-in potential, everything is given. You will be able to calculate it easily. Shall I move ahead? Okay. Okay, so this question says depletion region in an unbiased PN junction, that means at equilibrium, is made of what? Quickly let me know the answer to this. This is easier now. Sorry? Hmm. Yeah, exactly. So there will be immobile positive ions on the N side and immobile negative ions on the P side. So option C is the correct answer. Okay, let's move ahead. Okay, so it says that we have IV characteristics of a silicon diode, which is shown in the figure. We need to calculate the dynamic resistance. So resistance is nothing but what is the Ohm's law? Change in voltage by change in current, right? So we just need to find the slope of this and we'll be able to find this resistance. So we have already been given the value. So at V is equals to zero point 0.7, your current is 10 milli, and at V is equals to zero point 0.8, your current is no, it's 15 is the mid part of that. So at zero point 0.7 it is 10 and at zero point 0.8 it is 20. Yeah, so it will be actually zero point 0.8 minus zero point 0.7 divided by 20 minus 10 milliamps. So this is zero point 0.1 by 10 milli. That means 10 square 3. That means 10 ohms, which is option B. Is this clear? Okay. So let me also quickly explain the metal semiconductor junction, since we have not done that, and this is also a very important topic. Yeah. So we have metal semiconductor junctions. As the name suggests, one side would be metal and one side would be semiconductor. So now semiconductor can be either P type of or N type, right? So let's do one, maybe you'll be able to understand. So we have two types of junctions. One we what we call as Schottky and one we call as ohmic. Ohmic means we have a like a resistive nature of current. That means the current will easily pass. And Schottky is like a barrier. So we will feel some barrier while passing the current. So let's take an example. Let's say we are taking a metal and N-type semiconductor junction. And for this case, I am also taking the work function of metal then greater than that of the semiconductor. So let me try to explain what I've done. So let's say this is E vacuum and this is the Fermi level of metal. So metal Fermi level, I hope you already know that it is very inside the conduction band because there is a overlap of conduction and valence band, right? So let's say this is yeah, so this is EC, EV. So since we have taken, sorry, not EV, EF, EI, EV. So now what I was trying to say, so this was work function. We already know that this is the difference between the Fermi and vacuum, and this is phi s. So I've taken the case when phi m is greater than that of phi s. So how do you think the electron will flow from semiconductor to metal, right? But we already know that metal is already having excess of electrons. So what will happen? This will go down, right? Okay, let me add one more page. So if I try to make it, what will happen? The EF will align since I have not applied any voltage, and at the junction we'll have something like this, right? So you'll see that there is a huge barrier here, sorry. So there will be a lot of, because we are talking about N type here, there will be a lot of Nd plus ions. So this barrier is what is causing it to be a Schottky contact, right? So if we take a metal anti-semiconductor and for the case when phi m is greater than that of phi s, this is nothing but a Schottky contact because it feels a lot of barrier. Is it clear? Yeah. So you see now we have a lot of electron here and it wants to go from here to here because metal already had a lot of electrons, right? But now the metal is feeling the barrier because the work function of this was less than that of, so this will go down, right? So this is what happened. This has gone down. So this barrier is what is causing it to be acting like a resistance, not a ohmic contact. I mean the electron will not freely flow from metal to semiconductor, right? It should be opposite. The uh, electron should flow from metal to semiconductor to have a good contact, right? Because metal already has a lot of electrons. Is it? Yeah, everything will go down. I mean, this whole thing will go down. Yeah, so this is what I've drawn. So now, just to be clear, we can quickly take one more case when metal semiconductor still n-type. But now what we'll do is we'll take the phi m less than that of phi s. So what I'm trying to say now is, let's say this is vacuum, this is qm, phi, sorry, EA Fermi of metal. So this is phi m, right? And now what I'll do is I'll take the Fermi even below. So let's say this is the Fermi. Okay, so this is the EI, the dotted part. This is the Fermi. This is the EC, and this is the EV. So now the electron actually will flow from right metal to electron, right? Sorry, metal to semiconductor. So this part will go down, right? Are you able to understand this? Yeah. So if this part will go down, what will happen at the junction? We will not see any barrier. So now the electron can quickly come from. Okay. So let me make the aligned Fermi level. Yeah. This is the Fermi level. Sorry for this drawing. This is EI and this is EV. So now you can clearly see the electron will directly go from here to here. I mean, there will be no barrier. Sorry, the electron will go from here to here. My apologies. Since there is no barrier here, right? So this is what we call as the ohmic contact. Make sense? Yeah, so just to summarize this, so we have two types of contact for metal semiconductor. So one is that we have seen metal N type. In this also we have two cases when phi m is greater than that of phi s, when phi m is less than that of phi s. So this is Schottky, this is ohmic. Now we can also do the same analysis. You can do it at your homes for metal P type, in which you can take two cases when phi m is greater than that of phi s and when phi m is less than that of phi s. Yeah, so if you do the analysis correctly, so this will come out to be ohmic and this will come out to be Schottky. You can share the band diagram over email if you want. I can have a check if you have done it correctly. Is it clear? Okay. So I think we have covered most of the topics from this particular week and next also. So I've given a very basic introduction of BJT. So if you really want very deep introduction, you can see some of the lectures from Professor Dikshit. Because in next week, the main content that I want to cover is for the MOSFET. Because MOSFET is the actual most important topic of this whole course because that is what actually has been asked in all the interviews that you do or all the higher education also require the knowledge of. The main thing is the MOSFET. So I'd be starting maybe with the MOSFET, and for the deep understanding of BJT, you can see some of the lectures from Professor Vivek Dikshit. So yeah, that is all for today. I think I can stop the recording, and then maybe we can meet same time at the next week.